Hello, everyone, and welcome to today's webinar on quantum solutions to optimization problems. My name is Yuval. I'm Chief Marketing Officer of Classiq, and together with me is Yoni Zimmerman, who is a team lead and one of our quantum optimization experts. Hi, Yoni.
Hello.
So just a few words about Classiq, and then we'll get started. Classiq is the leading software company for quantum computing. We provide a development environment that allows organizations that want to jumpstart or accelerate their quantum computing programs to do it better and faster. Instead of having to work at more of the quantum assembly level, we provide high-level functionality that gets translated automatically into circuits that are optimized and hardware aware. And we'll show you some of that later. But what we'll do in this webinar, and Yoni, if you could move to the next slide, please, is we'll talk about the types of quantum optimization problems. What is quantum optimization? Why is it challenging to do it using quantum computing? We'll talk about the Classiq approach, how we look at optimization problems. We'll do some live demos of solving optimization problems using quantum. And then we have time for Q&A. Optimization, as you know, is used in many, many different fields, from finance to supply chain to others. So perhaps, Yoni, you could tell us a little bit about the types of optimization problems and how to think about them using quantum.
Yes, of course. Okay, so I'll take it from here. Thank you, Yuval. Okay, so let's start. We're going to talk a little bit about generally what is combinatorial optimization, and what kind of quantum algorithms we can apply for this kind of problem. Okay, so first of all, let's define what is optimization. In our definition, is just finding the optimal object from a finite set of objects. This is compared to continuous optimization, where it's an infinite continuous set. In continuous optimization, you can use the derivative and gradient-based optimization. But in combinatorial optimization, many times you have to go over all the sets just to apply some brute force search. And when the scale of the problem increases, this procedure just takes too long. The problem increases exponentially with its size, and we have to find some better ways to deal. So one main approach is using classical optimization, some kind of approximated solutions. We don't have to find the really best one, but find something that is good enough. Many possible classical optimization algorithms, such as taboo search, branch and cut, dynamic programming. So this is the area. We're going to show some examples, and then we're going to see how quantum information and computing can help this problem. Okay, so what kind of problems do we have? What is this objective function that we want to minimize or maximize? So here we just wrote a few examples. Let's see. So for example, if we have some cost, we go to a shop and we want to buy something. So we want the cost of our set of items to be as minimal as possible. If we want to travel from point A to point B, so we wanted the distance of the path to be minimal as well. It's just that the weight, the amount of the material, etc. From the other side, to maximize, there are other scenarios. If we invest some money, so we want to have the maximum profit for our portfolio. We want to have the maximum efficiency of some kind of procedure or supply chain we have in our factory, and many more examples. Let's go to something more specific. So we're going to get on the really most famous problems. Let's start to talking about it, traveling salesperson, maybe the most famous problem. Here, we just, here the story is we have many points or cities, and want to design a path that goes between all those points in such a way that the distance of the path is as short as possible. So overall, there is a factorial number of possible paths to go between n points. So this scales hyper exponentially. You have to apply some better approach. This is traveling salesman. Another problem also in the field of graph theory is max vertex cover. Here, let's see how it's defined. We have some kind of general graph. What is a graph? Just some vertices and the connections between these vertices. Those are the edges. And here we want to choose a subset of the vertices in such a way that we cover the most number of edges. In which way we cover? Edge is covered if one of its vertices is included in our subset. So this kind of mathematical formulation, what can we think as the real world story behind? We can think about some large building, maybe a school or an airport, and want to place security cameras between the corridors of the building. So let's say we have just 5 security cameras. We want to find the best spot to place those cameras. So this is just translate to max vertex cover problem. We're going to see this example. We're going to see and formulate in our platform, in Classiq's platform. Let's go on. Some more kinds of problems, also graph theory. So vehicle routing is pretty similar to traveling salesperson. Here, we don't have just one person going through all the cities. We have several vehicles, let's say trucks, that starts from a central point, the depot, and go through all the cities. And we want to minimize the depth or the cost of the fuel and all kinds of criteria. Another really classical problem is max cut. Here we have again a graph, vertices and connections and edges, and we want to split the graph into two. We want to split the vertices to 2 groups in such a way that the number of edges that cross between one group and the other is maximal. You can think of many stories that will translate to this kind of mathematical problem. And also this is like the standard problem in quantum optimization. Okay, so if you're gonna just to summarize how in Classiq we categorize the different problems, there are a few main families. So the most famous probably is the problems that are related to graph theory. There we have trees and covers and cycles and colorings, all sorts of terms in graph theory. Another important family is integer linear programming, ILP, where we have integer variables and some linear constraint, like x plus y plus c is less than or equal to some constant. This is a linear constraint. So what kind of problems translate to ILP? All kind of, let's say, a scheduling problem. We have many planes and want to somehow schedule their planning in the airport, or teachers in the university. And the prototype problem is this knapsack problem. We're going to talk about it later. 2 more families is constraint satisfaction problems and combinatorial structures. Let's go on. Okay, now we're going to start to present how we in Classiq suggest to solve this kind of problems. So first of all, we have to have some kind of common language, common tool on how we're going to define these problems. So we choose to use some Pythonic package. It's called PYOMO package. And it's just to define problems. It's an open source package. It's a clean and intuitive Python syntax. It's very descriptive. You can define almost every optimization problem that you could think of. So let's just go through a basic example in order to understand better. So what do we have in optimization problem? The first line is just the import of the package, and then we're going to construct the composing object, concrete model. All the other components are going to be just fields in this object. So which kind of component we have to build in order to define optimization problem? We mainly think of 3 components: our variables, our objective, in which we want to minimize or maximize, and our constraint. Constraint is what we define as a valid solution. So let's see how we do it. We can define a variable. We can give it some bounds. It can be maybe domain, maybe integer, maybe some float number. We can define a vector of variables. It's x3, and here range 5 just the indexes of the variables. Okay, so those are variables. let's see how we define objective. So here we just define a clear mathematical expression. We want to optimize x2 minus x3 to the power of 4 plus sinus x1. And pretty similar is the constraint, but here we have some kind of expression. For example, sum of x3. I'll just remind that x3 is a vector of variables, and we define it. We stress that we want it to be less than or equal to 2. Okay, so here was just like the basic components of a problem, and let's go on. So we are approaching to talk about quantum optimization. But let's first talk about what family of problems quantum optimization can receive. So the industry, they usually define those problems as QUBO. It's quadratic. The objective has to be quadratic in its degree. It's unconstrained because most of the quantum optimization algorithms, it's pretty complicated to deal with constraints, and it's binary. The variables have to be from binary domain. In our approach, we just expand this family to a broader family of problems. We call it PCIO. So we take the quadratic objective and enhance it to polynomial objective. And we also enable to put as many constraints as you want. They can be overlapping from many types and from many types. And our variables can be either binary or also integer variables. Okay, let's go on. So let's talk about quantum algorithms. We're going to talk about 3 quantum algorithms, 2 versions of QAOAs, and the Grover adaptive search. I just want to stress that these algorithms are embedded in Classiq platform. We have very customizable and flexible platform for these algorithms. But our platform enables to do much more. You can build your own algorithm to construct your own quantum building blocks and flow of the quantum algorithm, or either you can start with our own suggestion for the optimization algorithm, such as QAOA, and from them to develop your kind of modification. You can add some classical logic, some quantum logic, etc. Okay, so let's talk about the concrete algorithms. So first of all, QAOA was published in 2014. It's a prototypical algorithm from the family of variational algorithms, where they combine some quantum optimization and classical optimization. So the quantum part is defining some parametric circuit. We have to choose some parameters, and we're going to run this parametric circuit and measure the results at the end. And the classical part is just to define which are the best parameters to use. Okay, so this is just a general scheme of a VQE. And specifically, QAOA is more structured. The parametric circuit is built from layers, from repeated layers. Each layer is built from 2 sublayers, the cost and the mixer sublayer. The cost take the objective Hamiltonian and exponentiate it, and the mixer just change the solutions using the rotations around x-axis. Okay, so this is, we call it the first version of QAOA. Now for the second one, it was published in 2017. It's the same acronym, but the actual words are slightly different. And also the idea is slightly different. So here, the idea is how we're gonna deal with constraints. In the previous algorithm, constraints are plugged inside the objective Hamiltonian. If we have some constraint, we can penalize the objective in such a way that it won't go to invalid subspace. Here, we're going to do it differently. We're going to embed the constraints in the mixer subcircuit. If in the previous version, we just mix every string in the Hilbert space to every string, here we engineer it much more carefully. We really want it to retain inside the valid subspace. So here we have a few examples. From the left, we have mathematical expression, equality or inequality, and for the right, we have the quantum building blocks that helps us to be inside this subspace. Okay, the last algorithm is Grover adaptive search. Here is based on the famous Grover algorithm, where we can amplify the amplitude of some specific states. So we build quantum function, it's called the oracle, which identify which states are good and which states are bad. The good states are those that their objective is high enough, high above a threshold that we choose, and also satisfy all the constraints. So how are we gonna apply this algorithm? We choose a constraint, we build the Grover oracle, and then we apply Grover amplification. All the valid solutions will be amplified and the invalid will be diminished. In an iterative process where we update the threshold each time, we're gonna shrink our space just to the single highest or lowest solution. Okay, so
Great.
to you, Yuval.
Thank you. So now we'll talk a little bit about the quantum software challenge. Why is it difficult to implement that? So larger optimization problems require larger quantum circuits. You are going to need more qubits, you're going to need deeper circuits, and so on and so on. But the problem is that most quantum programming today is done very close to the assembly level. You could write at Qasim, you could cobble together predefined blocks, but these are not going to be optimal. These are not going to be optimized. These may not be relevant to a particular hardware that you want to use. You may need to switch them from one hardware to the other. You may need to change the circuit. So we believe at Classiq that with the existing methods of designing quantum circuits, it will be impossible to design larger and larger circuits with more qubits, with more depth, circuits that are necessary to solve these larger optimization problems. So what are we doing about it? Our approach is different. It is a higher level approach. We ask the user to define a high level functional model, basically saying, this is what I want the system to do. This is the oracle. This is the definition of the problem. And then we automatically explore a huge design space, look at many, many, many different options to come up with an optimized circuit that is also hardware aware, that takes into account the constraints that you care about. It may be the number of qubits in the computer, a particular gate set, noise model, connectivity, and so on and so on. Because we do it automatically, we can explore tremendously more options than a human can. And therefore, in many cases, we can reach a much better solution in a much shorter time. How did we go about it? Our inspiration was classical circuit design. This, what you see on the screen, is not a quantum circuit, it's an electronic circuit. You can see and or not gates. This has maybe 100 gates. And if I was just hired to fix this circuit or debug it or change it, I would have a hard time as is to understand what it does and certainly to make changes in it. And the Zoom call that we're all in is running on computers that have billions of gates. So how do I go to larger and larger numbers? Well, in electronic design, the solution was starting with high-level functional model, in this case, VHDL. So the circuit on the right is the result of automatic synthesis, automatic generation from the model on the left. The model on the left is human readable. You can start seeing that looks like it's a 16-bit design, that it has some kind of adder functionality. And I think that the vast majority of people would find the left side, the high-level model, much easier to debug, to change, to write than the right side. Well, we do the same for quantum. So on the left side, on this slide, you're seeing a definition, what we call a high-level model of the circuit. This particular one shows a Grover operator. You see the expression in line 9. This is the expression, the symbolic definition of the expression we're trying to solve. A plus 5 XOR B modulo 8 equals 2. Line 11 and 12 show the size of the quantum registers. And that's all you need to do. And then with a press of a button, we explore millions and millions of options and get to a synthesized quantum circuit, which you see on the right, which you can check, debug, execute, modify. It's very easy to go back to the original model and modify the constraints or modify the functionality and get something completely different as your needs change, as both the model changes as well as the hardware. And if you go to the next slide, Yoni, just to explain where we sit in the quantum stack, our synthesis engine accepts two inputs: the high-level functional model of what you're trying to do, and the list of constraints, which again could be the number of qubits or the gate set or the depth of the circuit, and so on and so on. Our output is one of the many existing languages. It could be Qiskit or Q# or Cirq or QIR or Bracket. And then it goes through the transpiler or compiler that you use today, and we can run it on pretty much any universal gate-based computer, whether on AWS, on Azure, on IBM, IonQ, or many others. And what happens as a result of this is that you, as the designer, focus on what you want to do, and the system figures out how to do it. And because we do that, that system allows you to build sophisticated quantum circuits in a scalable way, meaning you can start with a small problem that fits today's computer and very easily grow it to larger problems as larger computers become available. Because we go through numerous implementation options, we very often can reduce by orders of magnitude the amount of resources, the required resource, whether how many qubits or how many gates and so on. And that is very critical today because today's computers have very limited resources. We dramatically reduce the development time because we can go from weeks of development to hours or days, depending on the complexity of the algorithm. We believe that with us, you can generate circuits that could not be generated otherwise. And two other very interesting things, because the functional model is less about quantum and more about what you're trying to do, we've seen that people who are not quantum experts, but instead are optimization experts or finance experts or chemistry experts, can use the platform and generate very useful quantum circuits. So you don't necessarily have to be a quantum PhD in order to do very, very useful, powerful work with our platform. And last but not least, we do it in a way that allows you to build and keep your own IP. You can start building a functional library and you don't have to share it with anyone. You could then continue to enhance it over time and maintain the IP inside your organization. And Yoni, if you could, this all sounds great, at least to me. Show us how it works.
Okay, no problem, Yuval. We'll start with Knapsack problem. Okay, so let's just give some concrete examples to what Yuval and I have talked about. So we're going to talk about two problems, a knapsack problem and portfolio optimization, two standard problems in the field of combinatorial optimization. We're going to explain the problem. We're going to define it using Pyoma package, and then we're going to send it to our backend and to solve the problem. By solving, I mean to get the quantum circuit and also to execute on various backends. And then we're going to see if the problem converged or not. Okay, so let's talk about the knapsack problem. The story behind the knapsack is just, let's say I want to pick some items, and each item have its weight and its value. So I can pick or not pick it, or maybe pick some items from the same type, but I have to be constrained by the weight. Either the total weight is equal to the maximal weight, or it's just limited and it's an upper bound to the maximal weight. So this is my constraint, the weight, and the objective is defined by the value. I want to have the maximal value. So this may sound like a simple problem, but find out that if the variable is from a discrete domain, like a Boolean binary domain or integer domain, it's an NP complete problem. Okay, so let's see how we're going to define it. So we're going to talk about two versions. If the variable is binary, just pick or not pick it, 0 or 1, or it's an integer variable. We can pick several items from each type. Okay, so let's talk about a specific Pyoma code. So this is a Python function, Python method that we're going to generate our Pyoma package. It receives some numeric inputs, such as the value of each input, the weight, and the max weight. And then we're going to define the problem. So first line is just defining the overall decomposing object. Then we're going to define the variable. It's a vector of variables. Its length is equal to the amount of total items. And the domain is the binary. Then we're going to state our constraint. So we're going to use the inner product between the weights vector and our variable, and it's going to be equal to the max weight. So just the total weight is equal to the maximal weight that is constrained. Okay, the objective is just the inner product between the values and the variables. So it's just each variable is multiplied by its own value, and then I sum over this vector. And the last thing I need to stress is either I want to minimize the objective or maximize the objective. So here I choose a maximization problem. That's all. This is the way I just take our story, which is a knapsack problem, and formulate it to some Python code. Okay, so then in the next cell, I'm gonna build a concrete problem. So we're gonna choose some numbers for the weights, the values, and the maximal weight, and construct the Python model. Okay, the last thing is just to send the problem to our backend. And in this case, you can choose from many options. You can choose what kind of algorithm you want to apply. QA the first version with penalties, QA the second version with the engineered mixer. You can customize these algorithms. You can choose the amount of repetitions, the number of shots, number of iterations, all various optimization for this algorithm. And you can choose to have a look on few or several information. You can have a look on the problem itself, the Pyoma model. You can have an interactive visualization of the circuit. You can see the result and the parameters graph, and we're gonna see a few more visualizations. Okay, so first of all, the problem, we just have a summary, a textual summary of the problem. We have our variable vector, objective, and constraint. Okay, second thing is let's go to the quantum algorithm, the quantum circuit. Okay, so we choose a QA penalty, and we got a circuit. So here we have an hierarchical visualization. We can see the large picture, and we can dive in and to see each and every gate and how it is implemented. Let's show how it's look. So we have an initialization layer. Here is just a layer of Hadamard gates, just like the classical QA. And here we have many repetitive layers. Each one is built from cost layer and a mixer layer. The cost layer is a Suzuki trotter. We have just many RZ gates. Okay, and then the mixer layer is going to be a layer of rotation around x-axis. Let's go to the next version.
Just to ask,
yeah, of course.
These circuits were generated dynamically, right? As once you call the API, it generates the circuit. So even though it looks like a very complex circuit, it was generated automatically using the platform. Is that correct?
Yeah, of course. So we just send our optimization problem. We send all the preferences. We choose the algorithm, and then we're going to send it to our backend. If it's a very simple problem, you're going to get the solution really fast. If the problem is a little more complicated, it's going to take some time. This time is divided to the actual compiling. We have to run through large set, so it maybe take a few seconds. And if the problem is tremendous, it's going to take some time. And the second step is to execute the problem. You can send it to a real quantum hardware, such as IBM computers or Azure or AWS, and then you're going to run on some quantum computer. So it's going to take another time because you have to run many repetitions and many iterations to get some quality solution. Okay, let's go on. What else I want to show you? I want to show you our results. Here you can see that we got some logical result. We take the two first items. Those items are the items with the highest value per weight. And we have a solution distribution. Because it is a quantum algorithm, we don't get just a single solution. We get a quantum state, which is a superposition of many possible solutions. And we want it to have very high probability on the best solution. In order to get some good visualization on the probability, we show the histogram. Here in the horizontal axis, we see the cost, the value of each solution. And in the vertical axis, we see the probability to get that solution. So we can see that the algorithm converges pretty well. We get the most weight in our right side of the graph, the highest value, but yet it's not 100%. If we want, we can apply some more iterations, some more layers in order to really converge this quantum algorithm better. There are many possible customization. Here we have our parameters. We chose to start with linear schedule. The betas, this is the parameter of the mixer, are decreasing, and the parameters of the cost sublayer are increasing. This stems from the adiabatic quantum theory. Okay, let's go to some more complicated problem. So it's again a knapsack problem, but now we want to concentrate on the integer version of this problem. So we don't have to change a lot. We just have to change the definition of the variable domain. So from the binary domain, we change to non-negative integer, we define the bounds, and we can keep on. And here we also change from equality to inequality. Okay, we can choose some numbers. I chose less, just two items and not 5, because the circuit will be very large and I want to show you. But again, you can send as many items as you like. The algorithm is scalable, and we send it to our backend. So here we choose the other algorithm, QAway mixer. We want to show the circuit, show the results, and show the convergence graph. Let's go to the circuit. Okay, so here is already the hierarchical representation. I opened it a little bit. So first we start from a valid solution. We have a solution for both variables, x0 and x1. The solutions are just 0. And then we have the mixer, cost mixer, and so going. Our specific mixer in this case is kind of an interesting idea. In what way we're gonna engineer a mixer that satisfy constraints such as x plus y is less than 6. We're gonna mix each variable separately. So we're gonna mix first x0 by calculating the new bound that is defined by y. So if we have x plus y less than 6, the new bound for x is 6 minus y. So we're gonna perform some arithmetical expression. We're gonna have subtraction and multiplication by -1. At the end, we have the new bound for x0, and then we're gonna mix our variable. After that, we're gonna uncompute the arithmetical expression. The arithmetics that we use here is also done automatically by Classiq. We have powerful arithmetic engine which can compile every arithmetic expression you have. Okay, so this was a QAway mixer on Knapsack with integer variables. Let's go on. One more thing, we have the histogram, and we can show the energy conversions. So this is the classical iterations of the variational algorithm. First, we start with some value, and then we're gonna improve the value until it converged. Okay, let's go on to portfolio optimization. What's the story behind this problem? This problem comes from the financial sector. Many institutions and people, they want some mathematical way to know how to invest their money, their asset. So one model that is talked about for many years is the basic volatility minus return model. We want to calculate the volatility. It is the risk of the portfolio. We want to calculate the return, the expected return of the portfolio, and want to strive for the minimum of the minimum of the difference between the risk and the return. In such a way, we can lower the risk and maximize the return. Okay, so how are we going to define it? So we're going to define x to be the number of assets from each type. Again, it can be binary or integer or even negative numbers. If we do some short selling, we have the expected return for each asset. We're gonna denote it as mu vector. We have the correlations between each two assets. It's the sigma. It's a matrix sigma, and then we're just gonna minimize this expression. So this version doesn't have any constraints. We can make it more realistic if we add some constraints. Let's say we have some total budget that we can spend. We cannot buy each asset. So this total budget is translated to this kind of mathematical expression. The sum of the variables is equal to the budget. If we want to spend it all, if we don't want to spend it all, it's an inequality expression. Okay, let's go to problem definition. It's very much the same. The only difference is the objective. Here we have inner product of the returns and the covariances and the difference between them. Again, we choose numbers, we choose the algorithm, we send it to the backend, and we get the same kind of circuits with penalties or with mixers as we get for the knapsack problem. We can see that here it's a minimization problem, so the problem converged. Again, some linear parameters. I think I'm done here with the demo, and I would like to hear some questions if you have. Thank you.
Absolutely. Thank you, Yoni. So just to recap, what we've done here in a few minutes is generated a whole lot of quantum circuits. These can be generated dynamically. These can be generated to meet specific constraints, to be optimized to particular hardware. So I think that one question that came from the audience was if you could describe the number of trajectories or trials in each simulation step.
Okay, so I imagine myself that simulation is if I have a quantum circuit and I'm gonna run it on a classical computer, so I have to use the simulator of quantum computer. So it depends on the problem. Either I can just run it with one iteration and get a solution, but usually if those are variational circuits, I have to run many iterations in order to choose the best circuit. And for each iteration, I need to have many shots in order to get the right distribution of the state. So I would say for this kind of small problems, few hundreds of simulation iterations are enough, but it will rise as the problem increases. I hope it answers the question.
Absolutely. Now, a lot of the algorithms that you describe, VQE, Quawa, for instance, are hybrid algorithms, right? They have part classical and part quantum. So does Classiq also take care of the non-quantum part? How does one work when they want to run a hybrid algorithm?
That's a very interesting question. So the basic ideas are such. We want to offer as much as flexibility to the user we can. So we can change the classical optimizer between the quite famous one like SPSA and Kobila. We're gonna also offer in the future to define customizable optimization. You can write your own, let's say, Python optimization and just plug inside the quantum circuit as a black box. This is the standard VQE session. More complicated hybrid algorithms such as QML are in our pipeline for future development. But for sure, we're going to do it.
Excellent. So just to summarize, optimization problems are everywhere. Quantum computers can help. And Classiq can help with that journey. Now, one of the questions that came from the audience is, how does one work with Classiq? We are a software vendor. Our job is not to to write the solution for you, but rather to provide you with the best development platform and all the assistance you need so you can write your own circuits, your own algorithms, and solve the problems. There's a saying, if you give a man a fish, they have something for dinner, but if you teach someone to fish, they have food for the rest of their lives. We prefer to teach you to fish. We prefer to teach you how to use the Classiq platform to express a quantum, to express a problem, an optimization problem in this case, in quantum speak, to optimize it, to run it on a variety of backends so you can choose which one is best for you. And so a typical process with Classiq often starts with a proof of concept, a few months where we install the platform, train you, work together on a particular problem. And then from then on, you have a software license that you can use to enhance that solution or solve additional problems. This has been a very successful approach. We by now have customers all over the world. And if you're interested in exploring quantum for your purposes, talk to us, visit us at classiq.io, and we'll be happy to help. Yoni, how much knowledge of quantum information science and quantum mechanics do you think is required to be effective with the Classiq platform?
I think it's a spectrum. So on the one side, you can get very valuable results without really being an expert in quantum information, as Yuval said. For example, you can know optimization problem. You can be some routing expert or supply chain from all kinds of industry. You can define your problem in your favorite optimization language and just to use quantum algorithm as you use classical optimizers. I think that most of the people don't know how their classical optimizers work. They just take the algorithm and apply it to their problem. So we think that many people will want to work this way, just apply some quantum algorithm from one side. From the second side, quantum information is still very much in its beginning. Every day there's a new idea, the field is very dynamic. So if you want to progress your own kind of algorithms, you have to have some deeper understanding of the field, but we really try to do it as comfortable as possible.
So just to wrap up as we get to the end of the seminar, we think that we're presenting a dramatic innovation, a dramatic improvement in the way quantum software is being written. Just like most classical software projects are no longer written in assembly language, just like most websites are no longer programmed in raw HTML. Instead of assembly language, you have higher level languages. Instead of raw HTML, you use Wix or WordPress or Webflow or something like that. We think that Classiq provides that same level of improvement. Instead of working essentially at the quantum assembly level, you can work at a functional model and get optimized circuit that's hardware aware in a fraction of the time, and thus be able to solve problems that you couldn't solve otherwise. Thank you very much, Yoni, and thank you all for participating today. There will be a recording available, which we will send to you, and please feel free to share it with anyone you want, and visit us on classiq.io for any additional information. Have a great day.
Thank you.